Hello, this is John Noguera. I am the Chief Technology Officer at SigmaXL. Welcome to our webinar, What's New in SigmaXL version 9.1, Part 2 of 3, Automatic Model Selection in Advanced Multiple Regression. Our website is sigmaxl.com. Feel free to connect with me on LinkedIn at this address. The webinar will be 1 hour. The 45-minute mark, we'll take questions. Please type those questions in, and when we get to that point, I will review your questions and do the answers. The PowerPoint will be available for download, as well as the data set that is used. In fact, the data set comes with SigmaXL. It is the customer data. And the workbook, the examples that I'm going through are all in the SigmaXL workbook, so you can go through those on your own pace as well. So everything that I'm going to cover here today is also included in the workbook. The webinar itself is being recorded and will be available for viewing in a couple of weeks. We do some minor edits and then post that, and that'll be available for viewing at any time after it's uploaded. And so with that, we'll start. Introduction, and then I'll talk about various automatic model selection methods, including forward, backward, stepwise, forward selection, backward elimination, best subsets, hierarchical option, and some tips. We will then continue with the example that we started with in the first webinar, using the customer satisfaction as a function of responsive to calls, ease of communications, and customer type. And then we'll do questions. So, a recap, the typical approach to building a regression model involves the removal of terms with p-values that are greater than 0.05 or 0.1, resulting in models that are good, but not necessarily best. In this webinar series, we review metrics and methods that maximize the chance of building the best possible model, with important terms kept in the model, unimportant terms removed from the model, and provide maximum prediction accuracy. All right, so that's the goal, is basically to build better models in multiple regression. And any formulas that are presented will not be discussed in any detail. So we're going to start with the classical automatic model selection method, which is known as stepwise. And it is both forward and backward. And the way this works, you start with an empty model. Terms are added or removed from the model one at a time until all variables in the model have p-values that are less than the specified alpha to remove, and all variables that are not in the model have p-values greater than the alpha to enter. So the stepwise process either adds the term which is most significant or removes the term that is least significant in the process. It does not consider all possible regression models, so that's one disadvantage of the method. Note that the independent variables can be continuous or categorical or both. If it is a categorical predictor, it is treated as a group. So it's either all in or all out. So if you have a 3-level categorical predictor like customer type, the automatic stepwise will consider all levels or none. In other words, the entire term is in the model or it is not in the model. And that actually reduces the number of possible combinations when we get to best subsets. Just a note on forward, backward, stepwise, this is really included for legacy purposes. It's not really recommended. There are problems with using p-values. As I mentioned in the introduction, you can build good models, but not necessarily best. There are issues of p-values that are possibly due to just type 1. You have, lots of terms in the model, and so you may have p-values that are false alarms. And While it works, especially with smaller models, it's not necessarily the best model, and that's what we want to look at are the alternative methods that are now included in SigmaXL 9.1. So forward selection. Forward selection, you start with an empty model, and the most significant terms are added to the model one at a time until all variables that are not in the model have p-values greater than the specified in alpha to enter. Terms that are in the model are not removed regardless of p-value. Okay, so that's one, again, use of alpha to enter is legacy. The method that we recommend, alternatively and preferably, are the criterion-based selection method. So what happens is the most significant terms are added one at a time, while at each stage the value of a measure such as Akaike's information criteria or R-square is monitored. If a minimum AICC is observed at a particular step, and this remains the minimum after 10 additional steps, or you hit the wall where all terms are in the model, then the model with the minimum AICC is selected. And remember, in the first webinar, I talked about Akaike's information criteria. It's based on the log likelihood, and it penalizes for terms that are in the model. So it's actually a very useful measure. We include AICC in forecasting as well, and it's recommended to give a good predictive model. Now, on the other hand, if you choose R-square, then maximum R-square. So minimum AICC, maximum R-square, and what you do is you say if you find a maximum and it remains a maximum for 10 steps, then the model with the maximum R-square is selected. So because it's forward, it still may miss. It's not an exhaustive process, but it is very fast and very efficient. So options for forward selection include AICC, BIC, R-square adjusted, R-square predicted, and R-square k-fold. So R-square predicted is that you remove one data point, refit the model, and calculate or predict that one missing data point, and then you go to the next one, you remove it, refit the model, and predict that missing data point. R-square k-fold is k-fold cross-validation, where you create 10 bins. You use 9 of them to build a model, and then you predict against the out of sample, and you repeat that process 10 times. And then you come up with an R-square k-fold. So these we talked about in the first webinar. So AICC, Akaike information criteria corrected, and BIC is the Bayesian information criterion. So you have all these options available to you as the criterion options for forward selection. Backward elimination, you start with all terms in the model, and then the least significant terms are removed from the model one at a time until all variables in the models have p-values that are less than the specified alpha to remove. Again, we don't really recommend, this is more for legacy, using alpha to remove, but you can use criterion-based selection as described in forward. And that will also, once it finds a minimum AICC or a maximum R-square, and that holds for 10 additional steps, then that minimum or maximum is selected as the best model. Now, best subsets. So I want to state at the outset that best subsets is really the best methodology. The problem with it, or the disadvantage, is the number of possible combinations. So if I have p terms, there are 2 to the p minus 1 possible combinations. So once you get up to like 32, this gets very, very, very big. And that hits a wall, and typically best subsets is not viable for more than 32 terms. A criterion such as AICC is specified, and the model that results in the minimum AICC is selected. So what we do in SigmaXL is that if there are 15 or fewer terms, then all possible combinations are explored, and we call this exhaustive. Now, if you have more than 15, then we use the powerful Medako solver. Medako stands for Mixed Integer Distributed Ant Colony Optimization. I'm not going to get into the technical details, but it's a very powerful discrete optimizer that we use in DiscoverSim. And we licensed that technology. That was actually developed for the European Space Agency to optimize interplanetary space trajectories. So it is a very powerful optimizer, and it will very quickly solve all possible, well, actually, it's not an exact solution. It can't guarantee an exact solution, or a best solution, but it's going to be close to best. And it's a very useful, practical approach to dealing with this problem of large number of predictors and using best subsets. Let's say you have predictors and you have interactions and you have quadratic terms, and you want to consider all these in best subsets. With SigmaXL, you can do that. This Monaco will kick in and give you an optimal solution, not necessarily best as compared to exhaustive, but will be very close to best. So the criterion options, best subsets, include AICC, BIC, and R-square adjusted. Now, because of the computation times, because you're literally doing millions of possible calculations, we cannot use R-square predicted or R-square k-fold. AICC and BIC are much faster computationally. So what happens is then on the final models that are selected, these R-square predicted and R-square k-fold are reported. So you get them in the final report, but they can't be used to actually determine which model is the best. Now, as I mentioned in the first webinar, asymptotically, R-square predicted and AIC are equivalent. So it's not a big disadvantage. And in fact, what we recommend is that you use both AICC and BIC and then compare the models. So another important point here on best subsets report is that there are two options. The first is best for each number of predictors and best overall. Best for each number of predictors provides the most information, but it takes longer to compute. So what it does is it will say, okay, what's the best for one predictor? What's the best model for two predictors? What's the best model for three predictors? What's the best model for four predictors? And then you have a nice table and you can go through and you can compare and you can see the model getting better and better and where things start to degrade because you have too many terms in the model. And then you have the best overall, which simply says, okay, I'm going to use either the exhaustive or the discrete optimization and then pick the very best, or if you want the very best 2 or 3 or 4 or 5, whatever number of models you would like to look at, you can put that in. The default is you look at the best, or you look at the best for each number of predictors. You can put in a time limit. The default is 300 seconds, so 5 minutes. When you're doing best subsets with lots of terms, you may want to increase that if you find that it actually does hit the wall or does hit the time limit. Then you could increase it, give it more time, and it might find a better model. So as with the stepwise, the independent variables can be continuous and or categorical. A categorical predictor is treated as a group, so it's either all in or all out. You have a hierarchical option. This constrains the model so that all lower order terms that comprise the higher order are included in the model. So if I have, for example, an A-B interaction, then that means that both A and B must be in the model. And this is the default, and it is recommended that you use hierarchical. So these are just some additional technical details. I won't get into that with forward stepwise, backward elimination. We'll leave that. Okay, so some tips. There are a lot of options here, giving the user flexibility for model refinement. And as I mentioned, it's very easy to use recall dialog and try different things out and see what you get. But just want to give some guidelines, best practices, recommended settings. And the first is forward selection with AICC, BIC, or R-square predicted. Actually, of the three, I recommend R-square predicted because, again, that's your leave one out cross-validation. So it's a very nice way of doing it. And when you're doing forward selection, you don't have the time constraints or the time computation issues that you do with best subsets. So forward selection with R-square predicted is good. It's fast, and it will either minimize AICC, BIC, or maximize R-square predicted. As I mentioned, it does not consider all possible models. Also recall that AICC and R-square are recommended for the best model prediction accuracy, and then Bayesian information criteria is recommended for model parsimony. Do both, all right? Or do all three, and you can compare the models. It's pretty quick and easy to do that. Then best subsets, the setting we recommend is 1 for each number of predictors. So you're going to get one model for each number of predictors. So if I have 15 potential terms, I'm going to have a model for 1 term, a model for 2, a model for 3, and so forth. And then use either AICC or BIC with hierarchy checked. This can be slow, but gives a very useful report of the best model for each number of predictors in the model. And of course, we'll be demonstrating that. Now, some additional tips. It's important to ensure that the number of rows observations are sufficient to estimate the number of selected model terms. Now, we do have automatic checks for scenarios such as backward selection, where you have more columns than rows, and will automatically kick out the illegal columns. We also have, if you're doing forward, of course, you can actually have more terms than observations, but that's really not a good idea. Rule of thumb is that unless you're using data from a designed experiment, rule of thumb for historical data, there should be a minimum of 10 rows of data for every term selected. All right. So that's just a rule of thumb guideline. 5 might be okay, but especially when you have the situation where there are fewer observations than there are terms, you can very easily get to building models that are just noise. This is something that Jim Frost calls data dredging in his book, Regression Analysis, an intuitive guide for using and interpreting linear models. So he's got a really nice simulation study where he shows that, I think if I recall, he uses 100 terms, 30 rows of data with 100 terms, and he builds very beautiful looking models which are completely meaningless. So by the way, if you are in this situation, it's a good idea to do in-sample, out-of-sample testing. So you reserve some of the data for out-of-sample testing, and then you have the test ID, and then you can at least do a sanity check. But if you can avoid that, avoid the problem to start with by following this rule of thumb, okay? 10 rows of data for every term selected. And this is potential term, okay? It's not just number of terms in the model, but if you're doing automatic selection, the rule applies to potential terms. And then when you start getting into interactions and quadratic terms, it can quickly get quite large. So keep that in mind. So just a caution. When you're having automatic tools, they're very powerful, but they can build what appears to be a significant model that is just a nonsense model. All right, so we're going to now switch over to demonstrate. So now I'm in SigmaXL. I have the customer data open, and we'll go to statistical tools, advanced multiple regression, fit multiple regression model. Next webinar, by the way, the third webinar will cover the multiple response optimization. So we're going to go fit multiple regression model, use entire data table, and I'm going to use overall satisfaction. Recall that overall satisfaction, customer satisfaction survey using a 1 to 5 score. Survey results were averaged to obtain non-integer results. Here's overall satisfaction versus responsive to calls. So there's a pretty strong positive relationship. Overall satisfaction versus ease of communications, again, a strong relationship. And then overall satisfaction versus customer type, we see that customer type 2 has a higher level of satisfaction looking at the box plots as compared to customer types 1 and 3. So this is the data that we're using, and I'm going to put responsive to calls, ease of communications as my continuous predictor, customer type as my categorical, In the first webinar, we ended up removing customer type. So now I'm going to start off by including it, and let's just see what happens with the various automatic selection methods and what we end up using. I will standardize my continuous predictors. So I'm subtracting the mean, dividing by the standard deviation. So that converts those to z-scores, and that's better when you include interaction terms in the model because of units. If you don't standardize, you end up with problems with multicollinearity. And it's also easier to interpret the coefficients because then everything is based on the same units. I'm going to add a main effects plot, interaction plots. I'll go into options. I'm going to include my k-fold cross-validation. I'm going to stay with type 3 sum of squares. I'm going to assume constant variance. I am going to run stepwise regression. And I'm not going to use forward-backward stepwise. Okay, I said that was included for legacy. Here's your alpha to enter, alpha to remove. Similarly, if you go to forward, you can specify your alpha to enter. But what we want to do is we're going to use forward selection, select the criterion, and I'm going to use R-square predicted. All right, that's the one. Remember in my tips, I said R-square predicted is a good one to use for forward selection. You can also use AICC, BIC, but we're going to start with R-square predicted. Less pseudostandard error is not applicable. That's only used for saturated models. And we will go ahead. So, okay, forward selection, R-square predicted. Now, I am not going to turn on BoxCox Transformation at this point. I will do that at the very end, and you'll see why, because we want that as a variance stabilizing transformation. But we'll leave that for now, and then we'll click Next. And under available model terms with the main effects, I have the 3 terms, both the continuous and the categorical. I'm going to add main effect plus two-way interaction. So this gives me all possible two-way interactions. I'll select all. So this is the selected model terms, responsive to calls, ease of communication, customer type, responsive by ease, which is a continuous by continuous, responsive by customer type, continuous by categorical, ease of communication by customer type, continuous by categorical. And I will include the constant in the model, and now I'll run that. So remember now, this is forward, stepwise, and using R-square predicted. So the model it finally ended up with is the one that we ended up with in the first webinar, which is responsive to calls, ease of communications, and responsive to calls by ease of communications. That gives us an R-square predicted of 90.35. Okay, so we saw this. This is the model that we actually used in the first webinar. But now what I want to look at is the actual report. So this is my stepwise report. So what it did was it started with the first term that went into the model is responsive to calls. That was added. So I have one predictor, but 2 model terms because you have the responsive to calls plus the constant. R-square, 68.3%. R-square adjusted, 67.9. R-square predicted, 67. And you have your AICC and so on. And then the condition number, actually, of course, condition number 1 is very good. Remember, condition number greater than 100 is problematic. Now, the yellow highlight shows you which model was selected. And the double asterisk shows you the criterion that we chose, which is the R-square predicted. So remember I said I want to maximize the R-square predicted. So you'll notice that 90.35 is actually not the maximum. 90.42 is the actual maximum. So why didn't it pick number 4 instead of number 3? Well, the reason is because if you have ease of communication by customer type, then you have to have customer type in the model due to hierarchy. And when you do, you're actually less than. So we consider, remember we said we want hierarchy. So the rule of hierarchy has to be obeyed. So given the rule of hierarchy as a constraint, The best R-square predicted is this one that includes responsive to calls, ease of communications, and the interaction term. Okay, so that's our best selected model. And then we scroll over, we can actually look at a report. The ones denote that this term is in the model. And then actually an easier to read report is this one. That just tells you, that's kind of like a visual as to what's in the model. So you can see these are the three terms that are in the selected model at step 3. Okay, so Mallow CP, actually you'll notice Mallow CP is actually, remember Mallow CP, the best Mallow's number is the one that matches the number of model terms, including the constant. So that's this one here. If you look at AICC, the maximum R-square predicted actually corresponded to the minimum BIC. So that's interesting, the Bayesian information criteria. The minimum Akaike information criteria, it's this one because hierarchy is required. So I'm going to rerun this using best subsets. We'll do both Akaike and Bayesian. So the nice thing about this is that it allows you to compare. You can look at the different models. You can look at the different metrics. Yes, you want to maximize R-square predicted, but you want the model to be as efficient or parsimonious as possible. And so you have all of these report metrics that you can use to look at. So this ended up being the model that we used in the first. And you'll see here the stepwise method, forward hierarchical, and the criterion is maximum R-square predicted. Now, what I want to do now is I want to now demonstrate the use of best subsets. So that was forward selection. Now I'm going to go to best subsets. So I'm not going to bother with forward, backward, stepwise, or backward elimination. I'm going to go straight to best subsets. And best subsets, I'm going to use AICC. I'm going to use the default settings. And everything else will remain the same. And then we'll use, again, the model potential with all the interaction terms. Okay, so this is a more complex model. This is the one that minimized AICC. And it does include more terms in the model. And of course, you can compare the R-square and the R-square adjusted and the R-square predicted. But what we'll do is we'll look at that report. So this report now, this is not a stepwise report. This is a best subsets report. So what you have is for each. So for 1 predictor, for 2 predictors, for 3 predictors, 4, 5, 6. This is the best model selected for each of the number of predictors. And as you can see here, this is the Akaike information criteria is minimized. That's what we specified. So that's the model that's selected. And it just so happens that the R-square predicted is 90.25 is not quite as high as you would get. Well, actually, when we rerun, you're going to see with Bayesian information criteria, we'll get that slight. Actually, yes, R-square predicted. R-square predicted will be a little bit better when we rerun with Bayesian information criterion. So similar report in that you can scroll across and you can look at this is the model 5. So it includes more terms than the simpler model from the previous analysis. So that's another option. All right, it has more terms in the model. It's got an R-square of 92.73, but one could argue, well, maybe we can make the model simpler. And one of the ways to do that is to use Bayesian information criteria. So let's go and change. We're going to continue with best subsets, but instead of using AICC, we'll use BIC. Okay, now this is using the minimum Bayesian information criterion. Again, we use best subsets. We look at the report. We now see that the minimum BICC was selected, which happens to correspond to the maximum R-square predicted. And as I said at the outset, it's really easy to use recall and try different metrics, and then you can compare the various models. So in this case, model number 3, and then you can scroll over model number 3, and that's the model that, so it's responsive ease and responsive by ease interaction. Okay. I think we're going to consider that our final model. Even though Mallows is a little bit off, I mentioned that Mallows is not particularly useful. You're better off using AICC and BIC. Some practitioners do like Mallows, so we include it. Condition number, these numbers are pretty good. They're still low, less than 100. And you can look at the model overall. All the p-values are significant. We have a good R-square, good R-square adjusted, good R-square predicted, good R-square k-fold. All right, so everything looks great. So when we look at the residuals, we see, these are not normal. And, maybe we might be able to improve the model further. All right, and if we look at the model overall, we also see the Bruch-Pagan test shows that there is some non-constant variance. So the two things we can do, one is either to run a white robust standard errors, and that would be to uncheck this assume constant variance. I'm not going to do that here, but what I am going to do is I'm going to go with the BoxCox transformation. So the BoxCox transformation will solve for the lambda that normalizes the residuals. And in so doing, often addresses the issue of non-constant variance. All right, so we're going to go with this. This will actually work with Stepwise as well, so I may as well include that in the demo. Everything else is the same. And now I'm going to go ahead and run. Remember now, this is with the BoxCox transformation. So we actually end up squaring. And so lambda is 2. We're using exhaustive best subsets with minimum Bayesian information criteria. And our numbers look even better. Also, we no longer have a flag on the test for constant variance. So we assume now that the variances are constant. The residuals, well, they're still not ideal. But here's the thing, in real world data, often the residuals are not ideal. So it's just something you kind of work with what you've got and work with the best model. There's other things we could do here. We could do outlier diagnostics and so forth, but I'm not going to do that. All models are wrong, some are useful. So I think that's something to keep in mind, even though it would be nice to have perfectly normally distributed residuals, but they certainly look a lot better than the original ones that we looked at when we started in the first webinar. Okay, so that's the residuals. Main effects plots, you get some slight curvature. This is due to the squaring of the response in the BoxCox. Here are your interaction plots. Because of the different slopes, you can see that there is definitely a strong interaction effect. And if we go to the model, we can do contour surface plots. So this gives us a nice visual showing how satisfaction increases with responsive to calls and ease of communication. So you need to work on both those areas to improve your customer satisfaction. So the surface plot and the contour plots give you a nice visual interpretation for two predictors. If we had more, then there would be a matrix of contour plots produced. And the hold values would be whatever you put into the predicted calculator, it would use as hold values for the other variables not included in the contour plot. I'm going to do an optimization. So I'm going to maximize my customer satisfaction. And when you're doing optimization, one of the things you can do, if for some reason you want to restrict a predictor, if we included the categorical term, there would be a combo drop down here, and you could actually say, I only want to consider a particular categorical level, or I only want to consider a certain region for my optimization. I'm not going to change this, but just so you know that if due to economics, due to other factors, you want to limit the range that's considered for the optimizer. The other thing you can do, which is not applicable here, but if you had an integer constraint, a predictor was an integer continuous, then you would put that in as a 1. And when we do multiple response optimization in the third webinar, we'll actually see that. We'll be using the catapult, and the catapult has pin settings 2, 3, and 4. And so you want to use integer continuous, not pure continuous. So we'll leave that with the settings, and then we'll run optimize. This gives us our predicted response of 4.96, and we'll populate, and as expected, the predicted maximum satisfaction occurs when responsive to calls is 5, when ease of communications is 5. Okay, so there is one more thing I want to do, because I just want to show you that even though the residuals are not ideal, just how much of an improvement. So I'm going to take customer type out. I'm going to turn off BoxCox Transformation. I'm only going to look at overall satisfaction versus responsive and ease, and that's kind of like the basic model. And so when you run with this, and you look at the residuals, you can see that there's some really strong signal in here. And so the residuals that we looked at with our refined model, there's more dispersion. It's not it's still an improvement. So I just want to mention that while it's not ideal in terms of your assumptions, it's still something that you, again, as I mentioned, with real world data, it's often that you're not necessarily going to fully satisfy all the assumptions. There's also, in addition to the BoxCox transformation, you can uncheck assume constant variance, and it will use a robust standard error approach, so that can work. That's kind of like a Welch ANOVA, and I talked about that in the first webinar. So with that, I believe that is a wrap for the presentation, and I will now look to see if we have any questions. Okay, so Carlos asked the question, autocorrelation test. What is the interpretation of the displayed values, and how can it be corrected? So the Durbin-Watson test for autocorrelation has a Durbin-Watson statistic, and then we have the p-values. And if either p-value is less than 0.05, that means that you have significant lag 1 positive autocorrelation or negative autocorrelation. Then if you want, and by the way, this would only be done on the final model, because when you take terms in and out, often these statistics can change. So under advanced options, you have the ability to uncheck assume constant variance. And in the case of autocorrelation, it will use what is called a Newey-West robust standard error. Okay, so that basically adjusts for the autocorrelation. Now, another way of dealing with autocorrelation is to use ARIMA with predictors. So you can actually get into more sophisticated time series forecasting and so forth, but that's out of scope for what we're doing here. This is just a very straightforward, so that you're not violating the assumption of independence. But if the structure is complicated and there's seasonality and so forth, then you need to use ARIMA with predictors rather than advanced multiple regression. Basically, this handles a case where the report, again, back to the report, the Durbin-Watson test shows significant autocorrelation. So James, I imagine the noise to signal to noise ratio grows rapidly with terms to rows ratio. James, I think that's going to be a function of the data itself, how noisy the data is. And clearly, the more data you have using S over the square root of n concept, you're going to have more precision. So I'm hoping that answers your question. And then how is hierarchy related to the Bayesian information criterion? Those really are independent. You can have hierarchy on or off. You can use Bayesian information criterion, or you can use archaic information criterion. In our original discussion, so there's the Bayesian information criteria. So basically, terms in the model and the sample size. I mean, that's it for calculating Bayesian information criterion. But the hierarchy, the rule of hierarchy is a constraint. So you might not necessarily be getting the optimal Bayesian information criterion because you have to satisfy the constraint of hierarchy. So I guess that's a trade-off. But typically you would want a hierarchical model. Of course, you can turn hierarchy option off and then run it both ways. Okay, so the residuals after BoxCox with lambda of 2, how did you arrive at 2? So, James, the BoxCox is an automatic procedure, and it basically, again, let me just go to, this is the slide from the previous webinar that we did, BoxCox. So it considers the range from -5 to +5, and it's trying to normalize the residuals. But if it's stepwise regression or best subsets, we actually have an iterative process. And the way we do it for best subsets is we first do it using forward stepwise, solve for lambda, and then freeze the lambda value. But effectively, it's just what lambda value on the y gives us our best normality on the residuals. And it's just, just solves for the lambda. If you use rounded lambda, you're going to get a rounded value. If you use optimal lambda, you're going to get an exact value. Okay. Let me talk about the next webinar. So the final webinar in this series is coming up on Wednesday, May the 25th. So part 3 of 3, multiple response optimization. Okay, Carlos asked a question. Diagnostic checks are done only after selecting the best model. Carlos, that's just, just as a practitioner, you can look at the diagnostics at every step. I'm just trying to give practical guidance that makes this manageable. And obviously, if you want to check the diagnostics at every step of the way, you can do that. That's why I just say I recommend seriously evaluating the non-constant variance and the Durbin-Watson and not worrying about those until you get to your final model, because every time you add a term or take a term out, those statistics can change. So they're an actual function of the model. And so that's why I do recommend leave those concerns to the very end. Now, is that a best practice? This is what I do. Is it something that I just worry about being too quick to have to introduce BoxCox transformation or the more advanced, robust standard errors. So I would prefer to just leave those until the end on an as-needed basis. So hopefully that helps. All right. So thank you, James. James found this to be very useful. And I guess I don't see any other questions, so we'll call this a wrap. Don't forget, in a couple of weeks, this will be available for viewing, and we'll send out an email when it's ready. Please do sign up for part 3 of 3, multiple response optimization. We'll look at analyzing some designed experiments, and we'll do some multiple response optimization using SigmaXL 9.1. So again, thank you folks. Thank you very much for your participation, and we greatly appreciate your interest in SigmaXL. Thank you.